Hello everyone, my name is Morteza Bashsiz. I am a Linux system engineer. At this series of videos, you are going to find out how to be a good Linux system engineer. So if you want to know, stay with me. Welcome to LSE episode 7. At this episode, I will talk about the process of encapsulation in different layers of networking. Also talking about what is segment, what is packet, what is fragmentation, what is datagram, and what is frame in networking. So let's start it. Okay, we are here at this overview. And what is a segment? Let me describe it with an example. Imagine that I want to transfer these apples from a source to a destination. Of course, for transferring these apples, I will divide them to several parts and several units that I can carry. Imagine that I am not so strong to transfer them in one time. Then I will define an environment, a variable, a unit for myself to maximum transfer unit that I can carry in each time. Then I have maximum transfer unit, which at this example I define it 7. It means that I cannot transfer more than 7 apples in one time. So I will divide them in different groups that I can carry them . Okay, now I have 1, 2, 3, 4, 5, and 6 times. 5 times with 7 apples and 1 time with 5 apples. The same situation will happen in networking. For example, we have our data that we want to transfer it over network, and then our data will be divided to the several segments, and length of each segment is defined by a variable inside the operating system called MTU, maximum transfer unit, which is a variable that we define on our network interface controller. Let me show you the value of MTU on a Linux. Here I have a virtual machine that you can see the version of the kernel, and yeah, this is Debian, and to see what release of Debian installed on this virtual machine, you can use this command. It will show you exactly the version of Debian. And with a simple command, hyperlink show, it will show you that how many and what are the interfaces. And here in my interface, you can see the value of the MTU is 1500. Of course, you can have different MTUs for different interfaces, and the MTU, as I told, will be set on a network interface controller. And this value, 1500, is the default MTU for network interfaces. It doesn't matter that what is the vendor of network interface, what kind of device you have. This is default, and this is the standard for in networking, that all the interfaces will be configured on MTU 1500. And again, no worry about these commands and these things that you are seeing here. I will talk about the commands and tools in next chapters, but at the moment just concepts are important. And based on RFC 791, the minimum available amount of MTU in implementation of IP version 4 is 68 bytes. So in IP version 4, it could not be less than 68 bytes. So for MTU, we have a range from 68 to 1500, and it could be up to 9000 bytes. And we have a specific name for all MTUs more than 1500 bytes, and it's called jumbo frames. So when you have jumbo frames, that means that your frame could be in size of 9000 bytes, and you can carry more data in one frame. So it will increase the throughput and power of your network, and it is completely common and usual that you enable jumbo frames when you want to have a good throughput in your networking. For example, when you are serving storage or a data that, for example, like VOD content, that you are serving a video on demand and the streaming and like that, the throughput and the bandwidth and the performance of network is really important to having a better performance in your service. But you cannot enable jumbo frames in every network. It really depends on the hardware. The hardware that you are using, from your network interface controller, from your switch, from your, for example, if you are routing, your router, your cables, and the others. So your hardware must be sufficient if you want to enable jumbo frames in your network. Usually, jumbo frames will be enabled on 10G networks. So, yeah, when you have 10G interfaces, and also when you have a good cables and 10G switches, then you can have a 10G throughput in your networking. And okay, you can also enable the jumbo frames to increase your performance in network. There is also another metric, MSS, maximum segment size, that it's different from MTU, and I will talk about it at this video. But at first we should know some another things to understanding the differences between MTU and MSS. So if you remember the previous episodes, we had 7 layers in Osi model: the application layer, the presentation layer, the session layer, transport, network, data link, and physical layer. And segment is here, packet is here, frame is here. So segment, packet, frame. And when we are talking about jumbo frames, we are talking about the size of frame, the last step in encapsulation in different layers of networking. So this is the exact size of a frame that it should be transferred over the physical layer, and after that it will be converted to binaries, and it will be transferred over the physical layer. And for more details, let's continue and talking about the structure of packet. Here you can see the structure of packet. Packet is made from two parts, the header and the data or payload. And what we have in header of the packet, the first thing is version, and it is 4 bits of data that defines the version of the packet. If it was 4, so we have IP version 4, and if it is 6, and this is for IP version 6. The next part is length, and this is again 4 bits, which defines the IHL, internet header length. So this is the length of this header part of the packet. The next part is type of service, which is 8 bits binary number, and defines the parameters which are used in QoS, quality of service, like precedence, delay, throughput, and reliability. I will talk about them just here. I want to talk and show you that what is the structure of a packet. And the next part is 16 bits that defines the total length, including header and the data part. So this is the number that defines the length of your packet. And for these parts, identification, flags, and fragment offset, I'm going to skip them at the moment, and I will back again to this slide and talk about them later. Time to live, usually known as TTL. This is not something related to time. I mean, it's not millisecond, microsecond, second, minutes, and the others. It is an 8-bit value, which could be from 0 to 255, and it has some use cases, but the most important use case of this value in packet is related to defining how many hops your packet passed in routing. Imagine that you have two endpoints, A and B, and same as before, we have some routers between A and B. And when you want to reach from A to B, you have to pass the routers between them. Okay. One of these routers between A and B is configured wrongly, and the configuration is not correct. For example, this one. And let's see what's happened on your packet. So here your packet comes from A to this router, and then this router, and then this router. And what will happen here? For example, this router will forward the packet to again this router instead of the correct one, the next one. And again your packet will be sent to this, and again to this. And for example, again here and here. So you have an infinite loop in your networking between these two routers. Now the question is how we can fix this issue and how we can prevent from infinite loop in our network, and how we can detect that where is the problem. This is one of the use cases for TTL, and how TTL prevents from infinite loop in our network I will show you with an example. For example, if I define the TTL when the packet is generating in sender host, for example here our sender is this host. I want to send from A to B. I define TTL, for example, 64. And when I want to transfer my packet to the next router, this router will be checked. The packet that if the packet should be forwarded to the next hop, then the router will decrease the TTL once. So the router will decrease the TTL to 63 and then forward it to the next hop. And again, it will be repeated. For example, this router will decrease and forward, decrease and forward, decrease and forward, decrease and forward, decrease to 58 and forward, and here it will be decreased once again and forwarded and will reach to the destination. And here the destination B will be get a packet with TTL 57. Okay, at this case everything is working fine and everything was okay. So let's back to our issue with this example. What will happen here? Okay, imagine I have router 1 and router 2, and the router 2 is configured wrongly, and when a packet here with TTL, for example 62, comes to router 2, and it will decrease once and again return to router 1. Okay, and again and again and again it will pass to, for example, the router gets a packet with TTL 1. If a router gets a packet with TTL 1, it will not proceed the packet to the next hop, and the packet will be dropped when the TTL is 1. It doesn't matter which router gets the packet. If the TTL is 1, so the packet will be dropped. And now we can understand how TTL prevents from infinite loop in our networking. In the worst case, imagine that the TTL is 255. Okay, and here the TTL of the packet will be 253, and in worst case the packet will be transferred in a loop in 253 times, in 252 times, then the packet will be dropped. So here the infinite loop is broken and the packet will not be transferred between the routers anymore, and we fixed it. One another use cases of the TTL is when you are using trace routes. This is just as a heads up, or trace path. With these tools you can find out which routers exist between the source and the destination, and how many routers and how many hops you passed from your source to your destination. and we will talk about these tools in next chapters. And this was the definition of TTL in packet. And what is protocol? Protocol is an 8-bit digit, again from 0 to 255, that defines the type of protocol for the packet. For example, for this part you can see that if it was 1, it means that this is an ICMP packet. Or for example, it is 6, this is a TCP packet. Or for 17, it means that you have a UDP packet. Or for 27, it means that this is RDP. Or for example, for 38, it means that we have IDPR, sorry, and also CMTP packet. And about the header checksum, this is a 16 bits of data that helps us to verify the validity of the header. It's a checksum that we check that okay, the header is valid, okay, and or not. And the source and destination IP addresses is completely known, that each of them is 32 bits, and the source IP address and the destination IP address. About the options, this is 24 bits, and this field is optional. It's not mandatory to use, but you can use it for testing, security, or etc. This is completely optional. And the padding, it is a dummy field that this field is just for fitting the header size in multiple of 32 bits. And the data is what we want to transfer inside a packet. This is the actual data which should be transferred. And it was everything about the packet, the structure of the packet. And let's continue and again back to this slide and talk about these 3 left parts. And what is fragmentation? Fragmentation. Imagine that we have a router. This is a router, and we have 2 networks. The left side with MTU32 and the right side with MTU12. And what will happen if we want to send a packet from left side to right side? Imagine here is A and here is B, and we want to send the data from source A to destination B. And the packet is generated by MTU32 in source host, and it will be sent to the router with the same MTU, and the router, since the MTU is not 32 in right network, then the router will split the datagram to several smaller frames which are fit to the MTU12 in right side, and then send to the destination host. So the process of splitting a bigger frames to smaller ones, Actually, splitting a datagram to several fragments are fragmentation. What is datagram? Datagram is not something special. It's a definition. In a simple sentence, datagram is a segment of data which contains the source and destination. So if you have a data with SRC and DST, you have a datagram, and this is an abstraction. In a simple word, datagram is a concept, and IP packet is an example of datagram. So here, the fragmentation is the process of splitting a packet to several frames. It is fragmentation. And a frame is the smallest unit to transfer the data in data link layer of network. In a simple sentence, a frame is the result of the data link layer encapsulation before transmitting over physical layer in Osi model. The source and destination MAC addresses are stored in frame header. Now we can back to this slide and talk about these three parts. The identification. When a datagram or a packet splits into several fragments, IPv4 will assign the same identification for all fragments related to same packets. And this is how we can identify that which frames are related to which packet. So we described the identification. And what about flags? Flag is 3 bits of data which defines the fragmentation state. And for flags, we have 3 possible amounts. This one, 001 and 000, all 0. And okay, in binary, in decimal, this is 0, this is 1, and this is 2. When the amount is 2, it means that don't fragment. There is no fragmentation for these packets. So the packet, everything is in one packet, and there is no fragmentation. Okay, and when the flag is 1, it means that we have more fragments, and there is a fragmentation, and you should wait for more fragments, and this is more frames, and this is not the last frame. Okay, and when 0, we have no more fragments, no more, and yeah, the frame is the last one, and everything is finished. You don't have to wait for more fragments. So simple and so easy. And for the fragment offset, it is the offset of fragmentation, and it starts from 0. For example, we have a packet that we split it into 15 fragments. All the 15 fragments are have the same identification. The flags could be different, and for the fragment offset, it will be from 0, 1, 2, and up to 14. So we are done, and as a brief description, here we talked about the process of encapsulation. So in Osi model, we had 7 layers: application layer, presentation layer, session layer, transport layer, network layer, data link layer, and physical layer. Okay, and yeah, in transport layer we have segments, and it will be divided and encapsulated in packets, which also could be a datagram, and then it will be divided to different frames, and then here we have the physical address, actually the MAC addresses. Here we have the IP, the source and the destination, and here we have the segments, and all the process is called encapsulation. And we have fragments when we want to divide packets to frames, and that was everything that we talked about it. And here everything will be bit in physical layer over the physical devices. And for the last thing about MSS, maximum segment size, and the differences between MSS and MTU. When you have a packet, actually you have three main parts in network layer. You have your data, you have your TCP or UDP header. Imagine that this is a TCP, and you have IP header here. So this part is header, and this part is body, for example. Okay, MTU is size of the header and body, and MSS refers to size of the data, the actual data that you want to transfer. So the maximum segment size is part of the maximum transfer unit. This is the differences between MSS and MTU. And we are done with this episode. Thank you for watching me. If you liked it, don't forget to subscribe, and also like and comment and share with your friends to support me. See you in next episode. Bye.